Hi everyone, thanks for attending this talk. For over a year now, Thomas and I have been working on a new hardware design language called CoqPL. The most flexible way to write CoqPL programs is to write their ASTs directly in Coq, and we've written a few thousand lines of CoqPL code at this point. To make that tolerable, we've invested quite a bit in notations. This is what CoqPL code looks like. Bindings are introduced with let, conditionals with if, and functions with fun. Bit vectors are written like in Verilog with a size followed by a value. At first glance, this looks like a thin layer of notations on top of Galena code, but it's not. CoqPL is a deeply embedded DSL, not a shallow one, which means that the code on this slide actually denotes a complete deeply embedded AST with deeply embedded binders. Now, this is what the code on the previous slide parses to. Bindings are introduced with a bind constructor, which takes a string, conditionals resolve to the if constructor, and functions are a record containing their name, signature, and body. This is made possible by hundreds of lines of Coq notations. Since it took us a while to get it right, we thought it would be interesting to share some tips. We're going to go through three techniques: parsing with custom entries, parsing binders, and inferring dependently typed Debrun indices. I'll let Thomas start with custom entries.
Clément, oops, host disabled participant screen sharing on my side. I can't share my screen. Excellent, let's do that. Thanks, Clément. First, we will discuss how custom entries, a feature added in Coq 8.9, make it easier to work with deep embedded DSL in Coq. A part of this section is folklore knowledge about custom entries and retrievable tips, reporting from our experimentations. You can go next slide, Clément. Before Coq 8.9, one would often extend the Coq parser with standard notations to support deep embedded DSL programs. It would typically look like this. A notation capital if then else would generate the if then else constructor of the deep embedded language. The capitalization of if is crucial because one needs to worry about conflict with Galena. Coq needs to distinguish between the conditional from Galena and the conditional from the deep embedded language. Conflict with Galena were a first order concern when writing notation for a deep embedded language. One may want to add a notation square bracket A arrow B, but when using it, Coq will rightfully complain about it. Indeed, there are conflicts between the notation and the function arrow of Galena. This concern from Coq in general is legitimate, but when we are in a deep embedded language setup, having to worry about those interactions feels like we are considering problems that should not exist. Galena and the deep language are not one language, but two distinct ones, and the syntax should not conflict in any way, because they should structurally never be active at the same time. To avoid this kind of conflicts, the practical advice to the working Coq programmer is usually to use token and syntax for the deep embedded language that is as orthogonal as possible to Galena, but this has two drawbacks. First, we often end up creating creative looking operators so that are not so readable and writable. And second, while Proof General does know to handle Galena code properly, when we start using creative notations, it doesn't know how to neither highlight nor indent the code properly, which make it difficult to write programs. The miracle of custom entries is that conceptually it allows us to not just extend, but replace Coq parser. We won't need to worry about Galena construct. We will only deal with our own parsing rules. It goes like this. We declare a custom entries, here named Koika, from the name of our language, and we specify in which context Coq should start using this alternative set of parsing rules. Here, for pieces of code between double curly braces, Coq should start using the Koika parser, and so nothing to do with the Galena parser anymore. So now the Koika parser is empty, so we should define rules in it. So our first tip is that one should actually consider using Galena syntax as the syntax for the deep embedded language. This looks weird, but here we define an entry to pass what looks like standard Galena lets, but the rule produces a Koika bind constructor. The trick is that if this rule is only active in the Koika custom entries, it does not conflict with the Galena parsing. So from now, when encountering the let form within double curly braces, we will create a Koika bind. In our deeply embedded language, we have things like let, if, match, fun, structs. So for all of those, where there is a counterpart Galena, we can recycle Galena parsing and just make it generate Koika construct. This is an advice that goes against the previous methodology of picking syntax that minimizes conflict with Galena. Here we are sort of maximizing conflict with Galena by recycling Galena syntax. There are two benefits to that. First, the code is more readable and writable because of the standard looking syntax. And we inherit from the IDE supports syntax highlighting and auto-indentation, which is critical for usability. Our second tip is to add an escape hatch to leave our brand new parser, because actually sometimes we do want to leave it, and we do want to interleave Koika and Galena, but this interleaving should be in a delimited fashion. If we encounter backtick delimiters, we order Coq to leave our deep embedded parser and go back into Galena parsing. These tricks allow us to define readable macros. Here is a function that generates nested CoqA if from a list of pairs, condition, and AST attached to that conditions. Galena and CoqA syntax are interleaved here. At the top level, there is a Galena match, then syntax from CoqA between curly braces within the branch, but then using backticks delimiters, we re-enter Galena's world when we want to surgically re-inject an AST from Galena's world. While this kind of construction is standard when working with deep embedded language in Coq, using delimited custom entries makes the code significantly more readable and writable. Here, if we were to evaluate that piece of Galena function, we would get the desired AST. Now Clément is going to talk about how we handle identifiers, like how we manage to have this input which is not between double quotes, string quotes.
Thanks, Thomas. Let me move to a quality of life improvement that recently became possible. If we look at a typical deep embedded DSL in Coq, its binders look like this. Notice how each variable is wrapped in quotes? This is because if we want strings for variables in the resulting AST, then we need strings for the variables in the notation. Or, that is, we needed strings for the variables in the notation until LTAC2 came along. Let me show you how this works. This is the usual setup. One notation to enter a custom entry, one notation for let bindings, and one for variable references. But, using a small Coq library that Thomas and I wrote, all you need to automatically quote variable names is insert calls to identtostring, and it becomes possible to write variable names without quotes. The crucial part here is this identtostring notation. Let me show you how it works. There are two challenges. First, you need to capture the name before Coq realizes that it's unbound. Second, you need to convert that name to a string. We'll do that by pretending that the name is an identifier in a Coq notation. For the first part, concretely, identtostring is a notation that uses its argument, a, in an identifier position within a match. Putting a in that position means that Coq won't try to resolve it to an existing name. Instead, it will give that name to the thing being matched, TT, so any name is valid. Then, it calls a separate tactic using tactics and terms in the context of that match branch. The second tactic runs under the match branch, so its proof context contains a hypothesis of type unit introduced by the match. The name of that hypothesis is exactly the name introduced by the previous tactic, which is A. The tactic captures it as an LTAC2 identifier, and all that's left to do is converting that identifier into a string. This part is tedious but straightforward with LTAC2. You start with an LTAC2 identifier, convert it to an LTAC2 string, then to an LTAC2 array of LTAC2 characters, then to an array of LTAC2 ints. Then you convert each int to a Galena byte using a lookup table. At least that's the fastest we found, and by quite a bit. Then you convert the LTAC2 array into a Galena list, and eventually you convert that to a Galena string. Phew. All of this is done by a relatively small library that's part of CoqPL. It fits in a single short file, so you don't have to understand the details to use it. Okay, now parsing identifiers to strings is great, but in CoqPL's case, it's not enough. Let's look at a CoqPL program again. There are really two CoqPL languages, an untyped one and a dependently typed one. The typed one uses strong types in the AST to guarantee well-formedness, including for its deep embedded binders. Concretely, this means that variable references are not just strings. They need to point back to the binding construct that introduced them. For this, CoqPL uses dependently typed Debrun indices, which means that each variable reference includes a proof that the variable appears in the list of variables currently in scope. This is what the member HDM member TL constructs means in the AST. So if you look at the AST node for a variable binding, it looks like this. It has a variable named var_t, but also a proof, the member part, that this name is in scope. Of course, we don't want to write these proofs by hand, so we need to infer them automatically. To do this, we use a type class trick. First, we create a type class with a single constructor to hold dependently typed Debrun indices. Second, we give Coq a hint to resolve this class in the same style as Stage presented earlier today. Every time it's looking for a proof that the variable k is in the scope sig, we tell Coq to use assoc to look for k in sig. Assoc returns either a proof that k is indeed in sig or none, and must extracts the value from the option. With that, Coq can now automatically infer instances of this type class. Finally, we define the notation for a variable reference so that Coq will automatically try to infer the appropriate instance. And as a bonus, if we're afraid that this type class might fire too often, we can restrict it to only look at instances where the variable and scope are already known. We'll be releasing the identifier parsing library very shortly. It's a single file in the CoqPL repository right now, but we'll make it into a standalone library very soon. And you should check the extended abstract. There was one more trick in there to pre-print type checking errors for deep embedded DSLs. Thomas and I will be hanging around the CoqPL and POPL break rooms too, so feel free to find us at any time during the conference if you have questions. Thanks a lot.